Okay, so efficient computer, good place to start, I guess, would be just a little bit of background on the company, sort of when, why formed, any sort of key milestones to date, stuff like that.
Yeah, absolutely. So the at Efficient, what we're doing is very simply, we are building the world's most energy efficient general purpose processor. That's our reason to exist. We're obsessed with energy. We talk about energy. Energy is everything, is something we say. And that comes actually out of a longer history of research that was going on at Carnegie Mellon. I'm the CEO and co-founder at Efficient, also a professor at Carnegie Mellon University. And been there about 10 years, and for about 7 of those years, working with Nathan Beckman, another of our co-founders, and Graham Gobieski, now our CTO, but he was a PhD student back at CMU. Actually, the three of us were developing the underlying ideas that went into become the foundation of what we're doing at Efficient as part of a research agenda that we started basically when Graham started his PhD. So the genesis story, the origin story, goes back to years, 7, 8 years of research at CMU, where we gave ourselves this kind of ideological challenge. This was a really fun moment in research. We just said to ourselves, let's throw everything out. Let's start over. Let's do computer architecture from scratch, where what we want to do is create the most energy efficient general purpose processor that we can create. And so we just dumped everything. We started from zero. And we started to develop a new architecture as part of that research agenda. It was really fun. It was a really interesting arc to see that happen over that about 7.5 years. We got to the end of that when Graham finished his PhD, and we just had something in front of us that was obviously an important result. This was valuable. It was so good. We started seeing results from this research, and we said we have to go and do that again. We have to start over and do that experiment again to make sure that what we're looking at is real here. And we saw the value in it, and then we started to commercialize it through Efficient, and that's how we got to where we are today.
Okay, and the technology, or the name you've sort of come up with, is reconfigurable dataflow processor architecture. So that's the moniker, but can you give us a bit of the sort of nuts and bolts behind that, as much obviously as you can share with us?
Yeah, absolutely. So we do computing quite a bit differently than the way that a lot of your typical embedded CPUs or your microcontrollers that are running AI, DSP, those analytics, those kinds of embedded computing applications. We're quite different from the way the existing things in the market work. The way that we're different is that we're not what's called a von Neumann processor architecture. So von Neumann, sorry, it's a little wonky. I know it's kind of jargon. But the idea in a von Neumann processor, which is the way things have been done for a long time, is on every single cycle of the processor is going out to a memory and fetching in a new instruction, and then it sort of chunks through this pipeline of stages of execution inside. And I could go into more detail, but I won't. And the idea that we saw in that research, and then in what we're developing at Efficient here, is that ends up being really wasteful, because on every cycle you're going back to the well and fetching in basically a new command for what should my processor do. So the von Neumann processor architecture is quite inefficient because of that. And in addition to moving instructions around, von Neumann processors are really great at wasting energy by moving data around inside of their kind of inner workings of the chip too. We don't do any of that. We do something that's very different. So we have a processor that's a spatial array. So I don't have a visual aid that I can use to show you in front of me. I could get one out, but maybe we'll just talk through it instead. It's a spatial array. So this is a grid of processing elements. And instead of fetching an instruction on each cycle in advance, we have a really smart compiler. And it takes your program and it puts the instructions of the program down on each of the processing elements that make up that grid. And then our really smart compiler knows how to connect those up to respect the producer-consumer relationship between the operations that make up your program. And so now we can run that whole piece of your program, and we never have to fetch another instruction again. And the magic is in our architecture, the way that we've defined the operations, the way that we've defined the mapping between software down to hardware. We're, for example, explicitly encoding the interaction between operations, not just the operations themselves. And that's key. That saves us all of the extra effort of figuring out where to put intermediate values, fetching instructions, moving data. We're getting rid of those von Neumann overheads, and that's where we get all of our benefits. So if you measure it, it's a huge number. We go from von Neumann architectures, which waste, we studied this on the academic side, waste up to like 99% of the energy that they consume. And we get rid of a lot of that waste. And if you compare to, in market next best competitors, we're like 150 times less energy, and we can compile things directly from C code. So if you get rid of that von Neumann fat, this is what you're left with. And it's a very energy efficient architecture as a result of the things I was just describing.
Yes, and you mentioned a couple of times energy efficiency was the driver and is the main benefit. And I guess beyond that, that also enables pervasive intelligence that makes it a reality. So perhaps you can speak to that, why that's so important in the age where I guess artificial intelligence, as everyone is aware, is beginning to take over, shall we say?
Yeah, absolutely. So AI, ML, these are topics that we love talking about. And one of the things that I like to say when it comes to pervasive intelligence or putting compute pervasively in the world, which is another way of saying that, is that AI is more than machine learning. And I think that's something that some other approaches to doing computing sort of at the edge and beyond the edge have maybe taken a misstep on. AI is more than machine learning. So machine learning would be the sort of linear algebra that makes up the core of your machine learning algorithms, like convolutional neural nets and deep neural nets, things like that. That's a big part of artificial intelligence. But for pervasive intelligence to really work, to support applications like infrastructure monitoring, wearable applications, health applications, even things like space systems, small space systems, for that to work, you have to look at the rest of the application too. It can't just be the linear algebra part, the machine learning part. There's a whole broad stripe of other pieces of the application, like signal processing, data format conversion, data conditioning, general analytics. And actually, we've studied this pretty carefully at this point. If you look at full applications to drive intelligence, especially at the edge and beyond the edge. So think like infrastructure monitoring, sensor on every one of your water pipes or sensor on every one of your utility poles, things like that. It's about 50-50 or maybe 60-40, the split between machine learning in the artificial intelligence part of the application and all the rest. And so the point of me saying all this is you need a general purpose solution to computing. You can't just use an accelerator. If you just have an accelerator to support machine learning, you also need a fallback, which is like a CPU or something where you can do the rest of that. So my view is, and what we're really focused on at Efficient is generality while getting this high degree of energy efficiency, because that's very important for supporting this kind of diversity of different application workloads and the diversity of different computations that make up AI. Really, it's not just this one machine learning thing that makes up the whole world.
And in terms of the sort of sweet spots for it, you mentioned the edge, and I guess IoT is part of that. Is that where you're mainly focused, or do you see lots of other potential applications? I guess what I'm saying is, how far will it replace, as you already talked about, traditional compute? What's the potential, I suppose?
So the sky's the limit. First, there's a huge range of use cases for our architecture. Just to be concrete, in the near term, we're focused on the edge, on IoT systems up to the sort of mobile edge domain. And that's with our V1 and our V2 product. We focused on that because in general, energy is the most important problem facing computing today. That's something I say confidently. And I think for the next 10 years, we're going to be living in the era of the industry reinventing itself around the need for energy efficiency. It's been too long neglected, and now efficiency is going to be the most important thing and the only thing people are focusing on. And so if you look at those domains, like the IoT devices, low-end sort of edge devices, mobile, and up to even sort of higher-end edge, like edge cloud type devices, across that spectrum, you're often dealing with a device that is battery powered. And so with batteries, you're limited in a number of ways. One of them, you could think of just battery replacement effort converting directly into operational expense for whoever's going and running their application. So, I like to think about infrastructure. Infrastructure is huge, and it is a really important application. It affects everyone's everyday life. And if you get it wrong, it just doesn't work. And so one way to get it wrong would be to have an inefficient processor attached to an infrastructure sensor, and then you go and deploy 100 million of those infrastructure sensors. Well, now what you've done is you've just created a new kind of job where, some person in a truck needs to drive around and replace 100 million batteries, and that's a full-time job for a full fleet. And so it doesn't really solve anything. And so what you need to do is you need to provision the compute in these things so that it's efficient enough that you get 5 years, 10 years out of a small battery. And that's when you really hit the sweet spot with these applications. So going back to your question, focusing on the low end is where we see a huge opportunity for these energy efficiency gains to really have this enormous benefit. And it's not just incremental benefit for existing applications. It's really making it possible to do these kinds of enormous fleet applications where infrastructure is a great example. Looking forward, the architecture that we've developed is scalable. So it's not without additional technical innovation that we have to do. It's not without more understanding of how the technology scales. We have work to do, in other words, but we have confidence in the scaling path for our architecture. So we can take it from this chip here, which I'll show you. This is our first test SoC, and it's a full-featured SoC. It implements our architecture. You can see that little B wing on there, and that means that it's not just a prop. We actually had one of the foundries make it for us. We can scale from things that are about that size, focused on this IoT embedded mobile type market, and we can go up in a sort of V2 and V3 and beyond. And now this is projecting quite a ways into the future, and we're focused on these in our initial product offerings. But looking forward, the architecture scales to larger edge instances, or maybe even someday scaling all the way to the data center. There's nothing fundamentally tying it to these edge use cases. That's just where we see a huge benefit, and where we're able to make a big impact quickly.
Yeah, and in terms of the benefit, I mean, you've described, I guess there's a cost advantage. There's the practicality of applications you're enabling, as you say, particularly when it comes to the edge. I'm also wondering, I mean, sustainability, was that another thing? Because clearly the whole industry is under a lot of pressure, not only to support the digital world, and the AI explosions part of that, but also to reduce its carbon footprint. I can't remember, one of the big hyperscalers announced the other day, didn't they? I think their carbon footprint had gone up by 50%, which is a bit of a disappointing statistic when everyone's supposed to be heading in the other direction. So just, I suppose, your thoughts as to what contribution you can make to sustainability, as well as the other parts we've talked about.
Absolutely. So, projecting forward, like we were just talking about, just continuing that thought. If someday these things end up, these chips we're making end up in the data center, and they bring this kind of, category defining level of efficiency, it's really a new type of computing that we're doing here with this new architecture that we have. And the efficiency isn't like anything else that's out there. So say we bring those to the data center. Now we're driving down the energy consumption, and there's really big numbers at play there. So you drive down the energy of a data center, and you're cutting energy cost that's equivalent to a small town operating for a year or something like that. The numbers are really huge. Focusing more in the near-term use cases that we have in mind, there's two ways that I think this really hits, that have a relationship to sustainability. And this, by the way, is a big motivator for us. The idea of a more sustainable world, especially around IoT, is really important to us, and we're contributing there. So one is with batteries. Batteries are complicated to build, and you have to put the energy inside of them to begin with. So effectively, you're converting something in the environment into the energy that you have in the battery. And a lot of times, especially with devices, think again, like these infrastructure type sensors, a lot of them are like single use. And so you provision it to last for 10 years. And it's destined to, get thrown in the ocean eventually, get thrown in a landfill eventually. And that's horrible. It's horrible to think about that. The amount of battery waste that we're generating. There's been credible projections on the academic research that we'll see 1 trillion devices, IoT devices, by, I think it was 2030, something like that. If we have that many devices and they're battery powered, and even some small fraction of those devices are single-use devices that are going to be destined for the landfill, that's an environmental nightmare, a sustainability nightmare, and even just keeping up with supply chain management, circular supply chain management for all of those resources. If you want to just think bottom line, that's expensive. You have to go and figure out, where are we getting more batteries to put in these devices? So the battery problem is huge, especially when you think of fixed lifetime devices. There's another way of looking at it too, though, which is from the angle of what's been called in the literature embodied carbon. And so this is the carbon that you pack up, carbon emissions, basically. It's a stand-in for in general, the cost of the resources and the carbon emissions that go into the processes to create a chip. And those are quite high when you think about building a semiconductor product. There's a lot of steps, and there's a lot of, even just thinking fabrication, packaging, and so forth. And if you are designing around an architecture that is built to suit one application, now you need a chip for each of your different applications. And so you're essentially increasing the amount of aggregate embodied carbon that's required to support those applications. And so if you have instead the approach that Efficient has taken is to have a programmable solution. So now our programmable general purpose processor provides efficiency. So you're dealing with that first, kind of sustainability leg there, the battery idea I was describing a second ago. But also we're sort of eliminating the need for 4, 5, 6, 7, 8 chip or 8 chiplet or 8 components integrated into a complex SoC at higher cost in terms of carbon emissions. And so that drives down the aggregate embodied carbon for a range of applications of semiconductor products. And so Efficient's really addressing sustainability in 2 ways, through the battery costs and through this benefit to embodied carbon through its generality.
And I'm sure you must have had conversations amongst yourselves, but do you have any idea or thoughts as to just how much of an impact you either hope or expect to make with your new architecture? I mean, it's clearly very exciting, but any thoughts as will it remain, I won't say in a niche, but as you've indicated, in the early places in the IoT edge space, or do you really think there is the possibility for it to become a mainstream compute resource for the foreseeable future, I guess?
Yeah, we see huge prospects, and we see the ability for the product that we're developing, our V1 product, which is focused on the IoT and edge, and then our V2 product, which is further along into the future, focused on the sort of high end of the edge. That addresses a really broad swath of computing applications, from the tiniest beyond the edge IoT devices all the way up to sort of edge cloud scale devices. Fully general purpose. That means if you want efficiency, you don't need to put additional accelerators inside of your system that you're integrating. The chip that we've built and the efficiency that we provide applies to all of the code you're running on your system, and that's a huge benefit. That brings a huge potential benefit to a wide range of applications. So you talk about impact in the question. You mentioned impact. The biggest impact that we bring, especially with the V1 product, it's really an existential impact for the types of applications that I was describing before, where right now, because of the operational expense of maintaining inefficient computing solutions, that essentially that cost makes those applications infeasible today. And so what we do is we're bringing those applications into the world. We're enabling those applications, supporting things like really enormous fleet deployments where you need 5 to 10 year battery life, and you have a broad array of computing workloads that you need to run on each device. So I see the impact as sure, we're putting up energy efficiency numbers that are up to 150 times better than the next best general purpose computing part we can find in the market today. That's a huge and immediate impact for each customer. They see that benefit, they convert that into more features in their device, they convert that into extended battery life, and that's amazing, and we love that, and that's what we want to see when our products hit the market. Taking a step back, though, the broader impact really is the ability for the fleet size to grow. Scale is what's enabled when we improve the efficiency, and that's a typical conversion that we make in a lot of economic systems. Is you have higher efficiency, and that allows more growth with fixed resources. That's what we're seeing when we bring this kind of efficiency to general purpose computing.
And in terms of where you are now and the roadmap, I mean, you obviously you showed me the chip so that it's but what are you planning to do next? I mean, you're already talking to potential partners, customers, etc. Just whatever you can share as to how how you're going to take the initial idea and put it out there into the market, I guess.
Yeah, absolutely. So we have an early access program for a small stable of excuse me, we have an early access program for a small stable of early interested customers, and that's available now, kind of through direct contact with us. Available details on our website to get engaged with that early access program. And looking to the beginning of next year, in first half 25, we'll be sampling small volumes of our V1 product silicon with interested customers. That's a really exciting moment for us. We're hitting our tape out deadline at the end of this year. We're going to be bringing a product to market in the first half 25 and going to volume in the second half 25. So very exciting stuff to see this reaching the market in the hands of customers, supporting these kinds of applications. I can't talk about specific customer relationships that we have in this format, but I can give you an idea of the sort of key verticals that where we think there's a really a big impact because of the technology that we're bringing to market. I've mentioned infrastructure several times. I have a lot of faith in the idea that there's an urgent need for improvements in infrastructure, and technology is going to be a big enabler there. We are a key piece of that story. The efficiency that we have in our general purpose computing solution is going to make possible new things in infrastructure, whether it's power grid, whether it's oil and gas transport, and more general kind of industrial installations. Think, air compressors, generators, things like that. We'll have a level of visibility into these kinds of systems. It's unprecedented, and so that's enabled by these kinds of sensor devices that we make possible. So the industrial IoT, enterprise IoT is a huge opportunity space. A second space that I see a lot of opportunity is in wearables and especially implantable health technology, where the battery defines the lifetime of the device. And the upgrade path is pretty invasive if you're looking at something like an implantable device, where it's surgery to replace the battery. And so something like that, efficiency is essentially all that matters. And the compromise that you'd see in a lot of applications today is if you're so battery constrained, you just cut features. And that means your device doesn't have any AI, it doesn't have DSP inside of it. And so you're really limiting the scope of the application and the capability of the application. And that's kind of disappointing, just thinking about the technology. We have all this promising technology, and then, if only for the... So we're making it possible to do more with less. We're making it possible to do more with that limited fixed battery resource and those kinds of devices. So for a wearable, instead of charging your device every 3 days, if you're compute limited, then you can charge it, every couple of weeks or every month or something like that. For an implantable device, it's really a game changer because of, like I just said, you have to have an invasive surgery to replace the battery. The last area where I see a lot of promise, and this one's very exciting to think about as well, is in space systems applications. Again, here, energy is everything in these applications. And that means, you can do more inside of a satellite. If you have more efficient computing, you can do more inside of a satellite. Could be computer vision, could be RF spectrum processing. You can do that with smaller batteries, smaller solar panels, less complexity in the integration of the system. There's a lot of benefits. And so we've been looking broadly across especially these three verticals that I just described, but also a wide range of other application use cases. And we see a lot of promise, and we've been getting some really exciting early customer traction. One thing that it's maybe obvious, but that's particularly exciting about what we're doing from my perspective is we're general purpose. So throw at us what you want. We can support it. It's not an accelerator. It's not fixed purpose. It's not an ASIC. We're a general purpose processor. And so that's a very exciting moment. It's sort of, we put this out there early next year and say to the applications community, the developer community, the IoT community, the infrastructure community, let's see what you can do. That's really exciting to us. That's a really exciting moment for us.
Maybe just sort of finally, and widening out the conversation a little bit, just wonder if you've got any thoughts as to the overall compute market. I mean, it's quite exciting. Everyone's getting excited about AI chips, etc. And just bear in mind what you've introduced. Do you think a lot of companies will have to sort of rethink the way they're doing things? I know they're obviously already focused on that energy efficiency, but I know the sort of gains so far don't seem to be that significant compared to what you're talking about, and just, I guess, the efficient computers placed with it. I mean, just anything you'd like to say about that market and how much we might see it change over the coming years.
I think we're at a moment of great disruption for the computing industry, generally speaking. Computers are going to look in 10, 5, maybe 2 years quite different than they've looked for a long time. There is a shift toward AI chips, and when you go to something like AI chips, that's really limiting. You're tying the hands of the developer. They're not able to support all of the applications that they might want to support. They can support the fraction of those applications that are targeting the specific subset of AI algorithms supported by that chip. The world's bigger than that. AI is bigger than just machine learning, like I was saying before. And that's something that's part of the fabric of what we're doing at Efficient, is we're embracing the idea that, the feedback we've gotten from customers, the direct analysis of applications that we've done, AI is more than ML. And so a general purpose computing solution is really going to be necessary going forward. You tie that with another current, which is also really important, and it's again part of our core premise. Energy is going to be the only thing that matters. Perhaps it already is, and everyone's just catching up. For a long time, it was, let's take a 20% energy hit for an additional, squeak out the last 5% of performance, get more speed out of your chip. And that worked for a long time because we were getting new capabilities we'd never seen before. And that was actually the right thing to do probably for a long time. It enabled a lot of innovation. It enabled new applications. I'm thinking, in the 1990s and early 2000s, the transition to multi-core. These were huge sort of industry shakeup level trends. We're in one of those now, and that trend is driven by the need to redefine computing and redesign computers for energy efficiency. Energy is the most important constraint on our industry right now. And I don't like to speculate too much about the strategy or decision-making of other companies, but I can tell you very confidently that our strategy and our decision-making is focused on the idea that we can directly address the energy efficiency problem, which is the biggest problem facing computing today. And we can do it in a general purpose way. So we think that's the right thing to do. And there's an enormous amount of value unlocked with new compute technology like the architecture that we've developed at Efficient.
Okay, Brian, I mean, it's been great to chat and very exciting development you've talked about and shared some great thoughts on what's going on in the industry more generally as well. But really appreciate your time, and perhaps we can catch up later in the year, see where you're at. But for now, at least, thank you very much indeed. Thank you.
Yeah, it's been a great conversation. Thank you very much. Appreciate it.
Thanks again.